Right, so our speaker today is Jonah Gannon. He's from Swinburne University, and he'll be talking to us about ultra-diffuse galaxies. So take it away, Jonah.
And a little primary thing, 45 minutes is good.
Yeah, 45 minutes would be great.
Perfect. Okay, so hi, I'm Jonah. I'm going to be talking to you about ultra-diffuse galaxies and the stellar mass-halo mass relationship. I do want to say that this work isn't only my own, it's also done in collaboration with all these lovely people, particularly Jean Brodie and Duncan Forbes. Duncan Forbes was my ex-PhD supervisor, and Jean Brodie is my now boss and is the director of the Centre for Astrophysics and Supercomputing. And I'm also doing it as part of the Agate collaboration. So you may not have heard of the Agate collaboration before. That's something we're launching recently just to give our kind of science a bit of branding. Everyone seems to be doing it. There are all these collaborations popping up. So in order to help you recognize us, we are the Analysis of Galaxies Extremes team. Our names are down here, the primary members. And I know what you're saying when you, or know what you're thinking when you look at this. This is an astrophysics acronym, makes sense. The letters come from the start of the words, it's crazy. And to those of you who say that, we say that we're going to be a gateway to new discoveries. Terrible pun to get us in the mood for science. Anyway.
Might help us pronounce it. That was a great subject of discussion.
It is going to be a agate, or I think Anna likes agate.
Yeah, agate.
Agate. So, contents today, I'm going to be talking about the stellar mass-halo mass relationship. So I'm going to introduce it to you. I'll give you a quick thought experiment on it that I think motivates a lot of our science. I'll then move on to what an ultra-diffuse galaxy is. I'll focus in on globular-cluster-rich ultra-diffuse galaxies. Try and answer a few key questions for you. How many globular-cluster-rich ultra-diffuse galaxies are there? Can we really be certain they're in massive halos? And what have I learned about how they form? I'll then give a quick what's next in the field and conclude with my conclusions. So all talks should. So this is the stellar mass-halo mass relationship, only I'm lying, because if you look closely on the y-axis, the stellar halo mass ratio versus the halo mass relationship. This is a plot from Wexler and Tinker et al. 2018. It's an excellent review of the field. And what you're looking here is that star formation is most efficient in halos of mass about the Milky Way, 10 to the 12, and then falls off on either side, caused by various different feedback mechanisms. So for dwarf galaxies, it's thought that supernova, stellar winds, and reionization suppresses star formation and causes star formation to be less efficient in these lower mass halos. And in higher mass halos, you have this AGN feedback, which sort of suppresses star formation. And it's worth pointing out that, over more than a decade of science, through lots of different methods, such as abundance matching, parameterized abundance matching, halo occupation distributions, and kind of conditional luminosity functions, no matter which way you go about deriving your stellar to halo mass relationship, you tend to get a very similar result. And so we really think that this relationship encodes some of our most fundamental understandings about how galaxies form. A quick bit of housekeeping though, before I proceed with the rest of my talk. At times throughout the talk, I am going to be showing the stellar to halo mass ratio on the y-axis, but I will also just show the stellar to halo mass relationship. And so when you no longer divide through by the halo mass, you get this elbow that no longer has this U-shaped relationship. The galaxies below the relationship, I'll refer to them as being very dark matter rich. The galaxies above the relationship, I'll refer to them as being very dark matter poor. So hopefully it's not being hidden too much by the zoom. This is a nice little thought experiment to help you understand how we build up this relationship. So given the assumption that galaxy properties and halo properties are closely related, the most important constraint on the galaxy-halo connection is simply the abundance of galaxies as a function of stellar mass or luminosity. And you can build up this understanding by knowing the way in which we make this relationship. So first order, we're connecting something that's observable, galaxies in the universe, with something that's very dependent on your model, the availability of dark matter halos for those galaxies to populate. So this model can come from simulations, it can come analytically from the different types of dark matter you assume. First order, what you do is you go, this is the biggest thing that I observe in the universe, so I'm going to connect it to the biggest halo in my model. That's the next biggest thing. And you work your way down, connecting the biggest thing left in your observations to the next biggest thing left in your model, and you build up this stellar mass-halo mass relationship. So let's have a thought experiment. Say you have some kind of fancy new telescope that's going to survey the night sky, maybe the entire night sky, a significant fraction of it, to unprecedented new depths. I'm going to put up the Dragonfly telephoto array, which is already doing this in New Mexico. It's very relevant to the talk. But of course, LSST is absolutely going to do this in the coming years. Say when you do this, you start to find a whole bunch of galaxies that have been previously missed due to their low surface brightness. And I'm just going to put up this plot from Van Dock in 2015, which shows them discovering 47 new galaxies in the Coma cluster that had been previously missed due to their low surface brightness. Well, what we've now done is we've changed the abundance of galaxies from what's previously been observed. And so we want to ask ourselves, how is this going to change our understanding of the galaxy-halo connection? So we'll return to a little exercise. It's the exact same as it was before, but here I've inserted this extra low surface brightness galaxy, and we'll start doing our matching. You can see it proceeds completely as normal, right up until you reach this new galaxy that was previously unaccounted for in your matching. And what happens is that you have to assign this to a halo that already had a galaxy of ever so slightly less mass in it. And the effect, certainly not quite as extreme as this, but noticeable, is that you actually change the slope of the stellar mass-halo mass relationship beyond this galaxy that you're adding into it. And this, as I was showing in the introduction, we think that this slope is closely related to the level of feedback in these galaxies. So actually, just by discovering these new galaxies, we're starting to change our understanding of how efficient star formation feedback is in the dwarf regime.
Sorry, I realise this is a thought exercise, but
yeah. It's certainly dramatized.
yeah. Well, because that's the basic idea behind abundance matching, which is kind of one of the ways that we look at the stellar mass-halo mass relationship, but it's not the only way. And the other way is where we actually measure the stellar mass and we sample the halo mass through velocity dispersions. And I'm curious what happens if you take that more direct approach, where you see the same offset in the relationship that you're proposing.
Full disclosure, that's a significant fraction of my talk.
Okay.
So I'm a velocity dispersion person, so we're getting there. Okay, so what have I been talking about? Ultra-diffuse galaxies. So this is an ultra-diffuse galaxy, this smudge thing here that looks like I didn't quite clean it. It's very difficult to make out, you can tell. But there is a galaxy here, I promise you. This image is to scale. And the key takeaway from this plot is simply that this galaxy has a luminosity similar to this elliptical, but has a has a half-light radius much more similar to an Andromeda Milky Way-like galaxy. And immediately, even from this image, I think you can start to think about how these galaxies form. So because it's got a luminosity like a little dwarf elliptical, many people propose that if you just puff up a dwarf elliptical, it's the large end of the dwarf mass size or dwarf stellar mass size relationship. And so there's lots of different mechanisms like strong star formation, feedback, tidal stripping, tidal heating, which would get you a galaxy like this. But the other idea is, because this galaxy exhibits a very large size, perhaps it also exhibits a very large dark matter halo. Probably not quite as big as Andromeda or the Milky Way. I think we've got good evidence that that's not the case, but certainly much more than you'd expect given its stellar mass. So that's not really science though, so we'll just give you a quick scientific definition of what an ultra-diffuse galaxy is. This is a plot from the paper where they coined the term in 2015, Van Dock et al. It's plotting surface brightness versus half-light radius. You've got a population of everything in SDSS, which you see cuts off at about the surface brightness of the night sky, roughly 23 meg square arc second. You've got this population of Virgo dwarfs that have been previously observed, and they discovered an entire population of galaxies in this new region of parameter space. And so they've simply created a working definition to kind of cordon off this region of parameter space we study. They wanted it to have a large half-light radius above 1.5 kiloparsecs per square arc second and a low surface brightness, with central regions fainter than 24 megaparsecs per arc second. It's worth pointing out that there were a few galaxies that met this definition that were known about before, but the key takeaway of the last 10 years almost, this was in 2015, is that there are simply many, many more galaxies in this region of parameter space than we were expecting to find. And it's worth noting that because this is a very arbitrary definition, UDGs are an extremely mixed bunch. So this AGC phone number galaxy over here, sorry, these are both Hubble Space Telescope images of two ultra-diffuse galaxies. We've got this one over here, AGC phone number, which is blue, it's star forming, it's irregular, it's in the field. There are a few little clusters associated with it, but for the most part. You can see that it's contrasted quite strongly with this galaxy over here on your right, NGC 5846 UDG1. So this galaxy is red, it's quenched, its stellar body is well fit by a single Cirsig, it's quite smooth morphologically, and you'll also notice that it seems to have lots and lots and lots and lots and lots of these little blobs associated with it. Where this galaxy has 2 star clusters, this one has been measured to have 54. And for those of you who aren't aware, if we were to zoom in on one of these, you get these star clusters that are thought to be a byproduct of galaxy formation, kind of 100,000 stars in a nice little blob. And this difference in the amount of star clusters between the 2 galaxies is very, very interesting to us because it's thought that globular cluster numbers trace total halo mass. And so there's been this very tight relationship established for normal galaxies that have been previously studied. Here, red points are observations where you have an independent halo mass and globular cluster count. And you see that it's very, very well fit by this tight relationship, where if you count up the number of globular clusters, you can simply multiply it by 5 times 10 to the 9 stellar masses and get a reasonable estimate of the galaxy's total halo mass. This plot's coming from Berkeley and Forbes 2020. And so we do have one independent halo mass measurement for an ultra-diffuse galaxy. This comes from something like 4 nights of 10-meter telescope time on the Keck telescope. It's the UDG Dragonfly 44 in the Coma cluster, resides about there. So we do have some belief that we can use this counting of globular clusters to estimate halo mass, and in this way put those 2 UDGs I was showing you before into very, very different dark matter halos.
Sorry, with that plot, the really high mass end.
It's getting towards clusters and groups.
Yeah, but is it sampling around what's it sampling? Is it trying to sample intra-halo globular clusters, or is it just all the globular clusters associated with all the galaxies in that system?
It's getting towards every globular cluster in the Virgo cluster versus the velocity dispersion of galaxies in the cluster.
Okay, so it's everything associated with everything.
Everything associated with the system. Compared to down at the end where you have, it's almost a detection experiment where you get to the point where you only accept 1 or 2 globular clusters, expect 1 or 2 globular clusters. So if we return to our little thought experiment and our stellar mass-halo mass relationship, our kind of pseudo expectation was that in finding this new population of galaxies, we might start to see that this star formation feedback wasn't quite as strong as we thought, and that it was possible to have galaxies on this trailing edge of the stellar mass-halo mass relationship with more stellar mass and fixed halo mass than we were expecting. But if I take this very globular cluster-rich ultra-diffuse galaxies and I place them on this plot, they end up residing somewhere down here in this very, very dark matter-dominated, low stellar mass and fixed halo mass region. And while there are lots of theoretical ways of getting galaxies to lie off the plot to dark matter porosity at fixed halo, large stellar masses at fixed halo mass, there aren't as many ways of getting something to have very, very high fractions of dark matter and be very, very poor at forming stars. You essentially need your dark matter halo to fail, not form what you expect. And these are the galaxies at the extremes we study, and that's why we've called ourselves agate or agate, depending on how you like to pronounce it. So that was our thought experiment. What if we observe something different? But our new idea is, well, there's obviously something missing from our ideas of galaxy formation that doesn't include these massive failed dark matter halos. So what could it be? But before I get to what it could be, I think I need to convince you of a few things. First of all, I need to convince you that there are a lot of these globular-cluster-rich ultra-diffuse galaxies. If just one thing is a 5 sigma outlier out of 100,000 galaxies, then that's statistically expected. It's not that impressive. Can we really be certain they reside in these massive dark matter halos? To do that, we're going to have to measure some velocity dispersions, and then we can move on to this. How are they forming? What have we missed from our galaxy formation model by not including these galaxies? So let's jump straight in. How many globular-cluster-rich ultra-diffuse galaxies are there? So this is a plot that gets made whenever a kind of new type of galaxy is discovered. It's a very informative plot. It's plotting the halo mass of the environment versus the number of galaxies in that environment. And the reason we create this plot is because it tells us if environment plays a role in forming galaxies. So you find the number of galaxies as a function of the environmental mass, you fit a power law to it, as they've done here. If it's slightly superlinear, slightly above 1, it's telling you that you're more likely to find galaxies in clusters, which is also telling you that the clusters are what's forming it. If it's slightly sublinear, it's telling you that environments are destroying, dense environments are destroying the galaxies, and that they're preferentially found in the field. And so you can see here, based on this fit, it's ever so slightly superlinear, but many studies have found it to be slightly sub or slightly above. And so at this stage, I think it's very hard to say that there's any conclusive evidence we have that ultra-diffuse galaxies are influenced by the environment in which they form. I should say this is from a collaborative of mine, Steve Jansen's, his 2017 and 2019 papers. But the original question I'm asking is simply how many ultra-diffuse galaxies are there? So if we take one of these examples up here, Able 2744, it's a Hubble frontier field, a redshift 0.4, 0.3-ish, JWST early science field. It's got tens of thousands of galaxies. A reasonable estimate is between 30 and 40,000. We've found there to be 1,350 UDGs in the cluster, which means that roughly 5% of all galaxies in the cluster are UDGs. Or put another way, until we started having a look at these low surface brightness features, we were missing 1 in 20 galaxies in the cluster. And studies have now come along and had a look at groups and less dense environments. They're finding very similar numbers. By not considering the low surface brightness universe, you could be missing at least 5% of all galaxies in this low mass, or 5% of all galaxies in these environments. So that's the general question, how many ultra-diffuse galaxies are there? The next question we need to ask is how many are globular-cluster-rich? To answer this question, I'm going to go to my collaborator Duncan Forbes' 2020 paper, where he had HST images of a significant number of ultra-diffuse galaxies and non-ultra-diffuse galaxies in the Coma cluster, looking at their globular cluster systems and inferring halo masses of it. So this is the stellar mass-halo mass relationship. Here, ultra-diffuse galaxies are in red, dwarf ellipticals are in green and in blue. The normal relationship with 1 sigma errors, black line with dotted errors. And you can see that half of all the ultra-diffuse galaxies that they looked at in the cluster were very globular cluster rich, which caused them to have very high halo masses. And so my claim here is that this is much more than you'd expect if these are just randomly occurring outliers. If you believe the scatter in the relationship that was previously defined, this does not fit the stellar mass-halo mass relationship. And certainly when you compare it to more regular galaxies like the dwarf ellipticals and dwarf regulars of the same stellar mass, there does seem to be evidence that they reside in more massive dark matter halos. So if we're convinced that there's a lot of them, and we're convinced that a significant fraction of them could reside in massive dark matter halos, the next question we really want to ask is, can we really do this globular cluster number halo mass relationship matching? Is this a valid thing to do? So in order to do this, I created this Perseus cluster sample of galaxies during my PhD, where we had 5 UDGs in the Perseus cluster. We chose them to study, and we attempted to control for their size, their surface brightness, and for their cluster-centric distance. And the reason we do this is because all of these properties are known to correlate with globular cluster richness for previously studied non-UDG dwarfs. This is just a plot of them on sky in the cluster with the virial radius marked and everything color-coded by redshift. That proves that I'm not hoodwinking you. And down the bottom, you can see little image cutouts of each galaxy. Going from that, the galaxy we thought to be most globular cluster poor to the galaxies that are most globular cluster rich. And hopefully you can make out all the little dots associated with this galaxy, and there's very few associated over here. Might be a bit hard. So what we do is we go out there, we spend half a night of 10-meter keck time using the big IFU, the integral field unit, KCWI, to study these galaxies. We collapse the entire 16 arcsecond by 20 arcsecond field of view down into a single spectra over half a night, and we get these lovely spectra. So in black is the spectrum, in red is a PPXF fit. We fit the spectra to measure their velocity dispersion. So the first thing we do is we measure redshifts. That's great. It proves that they're in the cluster. Once you prove that they're in the cluster, you know they're not a foreground object. So you can then translate their measured angular size to a physical size based on an assumption of distance and confirm their status as that they are indeed an ultra-diffuse galaxy. But much more importantly and much more interestingly for our work, you also measure velocity dispersions. You measure the width of these lines. And for those who aren't aware, the dynamical mass in a galaxy is proportional to the velocity dispersion squared times the half-light radius. And so if we want to test that GC numbers correlate with halo mass, I think it's reasonable to assume that GC numbers should correlate with dynamical mass as well. That is to say that as I increase the mass of the halo, or as I increase the total mass of the halo, I should also, to first order, be increasing the mass of the halo in the central regions. And so this is a plot of our observations of these galaxies. So we have globular cluster number on the y-axis versus half-light radius, velocity dispersion, and dynamical mass. And the reason we plot these 3 properties is just because they are what goes into and the final product of the dynamical mass. You'll see that I have a line here kind of arbitrarily splitting my sample into those things that I think can be explained as just a normal dwarf being puffed up to a large size. And those things I think are best explained by a dark matter halo that's failed to form the stellar mass expected. And so we then go into this plot and we look for trends.
So, sorry, what's the reason behind that kind of argument? Is it just based on the number of globular clusters it's maintained, or?
So in this, it's solely the number of globular clusters. So we call things that are globular cluster rich. If you have more than 20 globular clusters, we say they're globular cluster rich. And you'll see that based on the scaling relationship, 20 globular clusters is a halo mass of 10 to the 11. And 10 to the 11 is ever so slightly beyond the 1 sigma scatter in the relationship, where probably it's more like beyond the 2 sigma scatter in the relationship at the stellar mass where essentially all of these reside. So things under this line are currently able to be simulated in modern simulations. Things above this line are problematic if they follow this relationship. So we look for trends across the 3 panels. I think it's quite hard to say you see any trend in this first panel, but that's because my sample was chosen to half-light radius or size match between the things that have few globular clusters and the things that have many globular clusters. I do think that there's quite a clear trend in velocity dispersion, where as you increase the number of globular clusters that we observe in these galaxies, you also seem to be residing in dynamically hotter systems. And the net effect of this is that you are also increasing the dynamical mass. So I think this fits with our first order idea that as you increase the number of globular clusters, you're also increasing the halo mass. And so I think we've got some reasonable evidence to believe we should believe this relationship.
Where did those other galaxies come from?
So, sorry, 5 are from my sample, 4 are literature galaxies. It's quite a disjoint sample because they require, half a night to a full night of 10-meter telescope time. Completeness is a large issue in the field.
Yeah.
Fair to say.
I'm really curious because I noticed that those ones that had kind of maybe they were more globular cluster rich. It's tricky to say with two galaxies, but they were the ones kind of further out in the cluster than the ones further in. There's probably not much you can say about it, but then I was curious whether the other 4 galaxies in that region were in similar environments or not.
So 2 are in the Coma cluster, 1 is in the Virgo cluster, and 1 is in the field.
Yeah, but on the outer regions or inner regions?
So out of the 2 that are in the Coma cluster, 1 is, I think, 0.4 of a virial radius. The other, there's reasonable evidence to suggest it's in a group that's actually being accreted to the cluster for the first time. The one that's in the Virgo cluster, I can't remember, which is bad because I was the one who made the measurement. And the one that's in the field is in the field. That's okay. So the second bit of evidence that comes from this type of work comes from an observational proxy for the stellar mass-halo mass relationship. So I'm going to put this slide up again, and all I want you to remember is that there's this characteristic U shape. But I also want to point out that observationally, we do not observe halo masses. This is not possible in the dwarf regimes to observe them directly or really in any regime. And we also don't really observe stellar masses. What we observe is luminosities and then make some assumption to convert them across. And so observationally, our proxy for the stellar mass-halo mass relationship has commonly been done with this plot, where you plot the dynamical mass within the half-light radius, a proxy for the halo mass of the galaxy, and the mass-to-light ratio within that radius, which is the proxy for the halo mass divided by the proxy for the stellar mass. Unfortunately, it's the other way up from the previous plot, so our characteristic U-shape goes the other way. So I established what's previously been observed with these black data points. You'll see it follows the characteristic U-shape. And then I put measurements on for a whole bunch of UDGs from the literature and from my own work. I think it's really quite obvious that there seems to be a population of UDGs that do not follow the stellar mass-halo mass relationship and reside in this region where they have very high dynamical masses for their luminosities, suggesting of very high halo masses for their luminosities, which provides further evidence that there are indeed this population of galaxies lying off the stellar mass-halo mass relationship, these very dark matter-dominated areas. So hopefully I've convinced you that there's a lot of them and that we have some reasonable evidence that they are actually quite massive. The question is, how are they forming? Well, one of the things we can do observationally is we can actually start to have a think about what type of dark matter halo these galaxies may reside in. So to do this, we're going to compare the dynamical mass we've measured within some kind of radius to idealized halo profiles with the total halo mass that we expect coming from the globular cluster system. The things that I'm plotting here in blue have very few globular clusters. We expect them to have halo masses less than 10 to the 11, maybe even less than 10 to the 10. And things we have in red have very many globular clusters. We expect them to have halo masses above 10 to the 11. And to first order, what I want in this plot is for red points to agree with red lines and blue points to agree with blue lines. So first we do it for cuspy NFW profiles, and I think it's quite obvious that these cuspy NFW profiles don't actually provide a very good fit to our data. There's quite large differences between what we're measuring the dynamical masses for these globular cluster-rich things to be and what you'd expect them to be if they had a cuspy dark matter halo. Instead, though, we can make the alternative assumption and say that these galaxies produce a dark matter core like is known to exist for many dwarf galaxies. And if that's the case, I think you get much better agreement from the total halo mass you expect, given the globular cluster system, and the dynamical masses we're measuring in their central regions. And so the conclusion I want you to take away from this somewhat complex plot is simply that if you assume that the total halo mass you get from the globular clusters is correct, cored dark matter halos are providing much better fits to our currently measured dynamical masses, UDGs. And this is quite important in the context of formation scenarios because very strong stellar feedback is known to cause mass outflows, which can core your dark matter halo and reproduce profiles exactly like what I'm plotting here. And also, chord halo profiles are less gravitationally bound in the central regions, which allows them to be more easily puffed up into larger sizes. We also want to compare the dynamical masses between the different kind of types of UDG we're measuring. So here I've got 3 types of UDG that I've shown you throughout this talk. We've got the very globular cluster-rich, smooth red thing that tends to be in high-density environments. We've got this very globular cluster-poor, smooth red thing that we also find in high-density environments. And we've got this globular cluster-poor, blue, irregular, star-forming field thing. And I'm going to add to them UDGs that have been simulated by the Fire and Nihao hydrodynamic simulations. Both of these simulations focused on very physics-intensive, isolated galaxy formation. And so my claim is that we expect the gas-rich and the globular cluster-poor things have a very similar dark matter halos, simply because if I get this and I throw it into a cluster, I'm going to end up with something that looks a lot like the globular cluster-poor things we're observing after a few giga-years of evolution. I also want to claim that because Fire and Nihao simulate isolated gas-rich UDGs, the masses they measure in their simulation should agree with the masses we measure for isolated gas-rich UDGs. And none of these should agree with the globular cluster-rich UDGs because of the very different dark matter halo mass that they have. So let's put the plot up. So here again, I'm plotting the radius from galaxy center versus the mass enclosed within that radius. Globular cluster-rich things are in red, globular cluster-poor things are in blue. H1 rotation curves for the gas-rich field things are in green, and the mass range of halos simulated by Fire and Nihao are in purple and orange, respectively. And so I think the idea we had that we should have globular cluster-rich things being in generally higher mass halos or high dynamical masses than both the gas-rich and the globular cluster-poor things is held out by this plot. I think it is obvious that in general, globular cluster-rich things have higher dynamical masses than the gas-rich and the globular cluster-poor things. I think our idea that if we get a gas-rich field thing, throw it into a cluster, you can reproduce something very similar to our globular cluster-poor things in the clusters is also held out by this plot. They have very similar dynamical masses. If you put it into a cluster, you can get this evolution in the similar mass halos. But the interesting thing to me, based on this plot, is that the 2 simulations that are simulating UDGs forming in the field seem to be producing dark matter halos much more massive than what we're measuring for the galaxies that they're simulating. Indeed, they seem to be in much better agreement with these very globular cluster-rich things that shouldn't be in their simulations. It actually gets more puzzling when you start to have a look at this in stellar mass halo mass space. So this is the stellar mass halo mass relationship. In brown and in grey are a couple of different observed abundance matching relationships. You have these gas-rich field UDGs where you get a halo mass via fitting to the H1 rotation curve of the galaxy. You have the observed globular cluster-rich UDGs placed on this plot via assuming the number of globular clusters accurately predicts the halo mass. And then you have the simulated UDGs put on this plot by measuring it out of the simulation. And so I think it's quite clear that generally all the simulated UDGs seem to just be following the stellar mass halo mass relationship. But this isn't in too good agreement with what we're actually observing for UDGs. There seems to be this very large scatter in UDG halo masses where you have these gas-rich field things that are forming stars very efficiently for their halo mass. But you also have these failed cluster things. And I must admit, it is still quite a bit of a puzzle to me how these galaxies reproduce the central dynamical masses, the globular cluster-rich UDGs, without reproducing their total halo masses. One possible idea is that these galaxies have all formed with chord halo profiles, whereas these form with cusp halo profiles. I have already shown you some evidence that that may be the case. So if we don't really think that simulations are quite getting these galaxies correct, then what we need to ask ourselves is how do we create a failed galaxy? how do we create these massive dark matter halo UDGs? And to me, there's these two key ingredients that I think help make it work. You have fast star formation, and fast star formation is known to create more stars in globular clusters. It's known to concentrate your supernova feedback, which produces a dark matter core. This increases your susceptibility to tidal forces, and the concentrated supernova feedback also helps produce a large size. But crucially, you need to stop these galaxies forming stars very quickly as well. If you continue forming stars very quickly, you end up with just a normal galaxy. You end up with a lot of stellar mass, not very, very little. And so you need to quench these galaxies early, you need to passively evolve them, and that'll give you your low surface brightness, which is the UDG definition. So this is work that's been done by one of our PhD students at Swinburne University. She's done SED fitting to lots and lots of ultra-diffuse galaxies across a range of environment. Here it's about 20. She's got another 40 soon to be published. And it's looking at the mass-metallicity relationship. The normal mass-metallicity relationship for dwarfs and more massive galaxies is shown by the various shaded regions. And here, again, she's cut her sample into things that are very globular-cluster-rich in red, and things that are very globular-cluster-poor in blue. And so if we expect to be able to explain things that are globular-cluster-poor as just large dwarf galaxies, I think that holds out. They seem to follow the mass-metallicity relationship established for normal dwarf galaxies, suggesting they could form in a similar way. But very interesting to us is this population of very globular-cluster-rich ultra-diffuse galaxies that have very low metallicities for their stellar mass. Indeed, they actually seem to agree with the theoretical mass-metallicity relationship for a galaxy at a redshift of 2.2, despite the fact that they're observed at a redshift of essentially 0. And so the suggestion here is that these galaxies formed very, very early, they quenched very, very early, and have not experienced any further evolution in their stellar population since a redshift of 2 and a bit. Exactly in agreement with our expectations, given our little toy model. The other bit of evidence for ultra-diffuse galaxies forming and quenching at a high redshift actually comes from their positioning in the stellar mass-halo mass space. So again, this is the stellar to halo mass ratio versus halo mass. There's the characteristic U-shape. And throughout this talk, I've been saying that ultra-diffuse galaxies don't follow the stellar mass-halo mass relationship. And that is true, but it's true with the caveat that they don't follow it at a redshift of 0. There is actually an evolution in this relationship across the edge of the universe. So at a redshift of 10, you start to have the first dark matter halos collapsing, and very quickly, the dark matter halos build and accrete and merge together, and actually galaxies grow their dark matter halo much more quickly than they grow their stellar mass, right up until a redshift of, this is redshift 6, redshift 7, not redshift 5, sorry. And then when you hit a redshift of 4/3/2, between this range, this is the peak of cosmic star formation in the universe. This is the famous Mandown-Dickinson redshift 2. The universe is forming stars very, very rapidly. And so it's at this redshift where the evolution in the stellar to halo mass relationship stalls. Galaxies become much more efficient at forming stars than they do at accreting more dark matter. And beyond this, it continues where they continue forming stars, and eventually it evolves into what we see today. And so if I place these very globular-cluster-rich ultra-diffuse galaxies on this plot, something that's a 4-5 sigma outlier at redshift 0 is only a 1 or 2 sigma outlier, not even an outlier if it's 1 or 2 sigma, but 1 or 2 sigma outlier at a redshift of 2/3, which is where we expect them to be forming based on their mass-metallicity relationship. So there does seem to be some really good evidence that these galaxies formed very quickly, very early on in a very massive dark matter halo and just stopped. Now, one key claim as to how this has happened is, well, we're finding a lot of these galaxies in clusters. Maybe that's just when they infell into the cluster. So you can quench a galaxy in a cluster and then it'll just passively evolve until we observe it today. And so in order to test this, we had a look at their phase space positioning of ultra-diffuse galaxies in various clusters. So this is the normalized radius from the cluster center versus the normalized radius, normalized velocity from the cluster mean. I've color-coded it based on regions from simulations of Rhee et al. 2017, where things in darker regions have infallen into the cluster at very early times in the universe. And as you move to lighter regions, things are being accreted into the cluster at much later times, more like today. And the scientific explanation for this is that if you infall into a massive cluster at early times in the universe, the cluster is less massive, it has a smaller gravitational potential, so you end up in colder orbits that are more centrally bound to the cluster than something that arrives later on. And so if our expectation is that these very globular cluster-rich things formed early, and were accreted onto the cluster early, quenching them, we actually expect the majority of them to be found in this very early infall region of the cluster. Whereas globular cluster poor things will be continuously being accreted throughout the age of the universe, and so should be scattered throughout the plot. So I apologize for the horrendous color scheme. This is as published. So here I've added a whole bunch of observations of UDG phase space positioning from the Coma, Perseus, Hydra, and Virgo clusters, and I've color-coded them by their GC richness. So things that are blue or have blue outsides are globular cluster poor, things that are red, globular cluster rich. And my claim here is that you can't really see a trend. It's not clear to us that on average globular cluster rich things are found in the center of the cluster, especially in comparison to these globular cluster poor things. It seems to be quite a scatter plot for both. And so I don't think it's obvious that globular cluster infall and quenching can explain how these galaxies form. So we need to start thinking of other ways of quenching these galaxies that isn't simply an accretion onto a cluster, especially as we find some in the field at present times. So just a quick summary as to why I think it's really important to keep pursuing this low surface brightness dwarf science. This is from a review of Nature Astronomy Review from Laura Salles, Baryonic Solutions and Challenges to Cosmological Models of Dwarf Galaxies. It's a review into what simulations are currently having the most trouble reproducing observationally, and they've split it into no tension, uncertain, weak tension, strong tension. And so I've been talking about widely varying dynamical masses, which is part of the diversity of rotation curves problem. This represents a new population of large low surface brightness dwarfs that were not previously simulated or known about, a diversity of dwarf sizes problem. I haven't talked about it in this talk, but there does seem to be a significant fraction of these galaxies that are quenched in the field. And so this is currently poorly explained by simulations. My entire talk has been about the stellar mass-halo mass relationship, so I hope I've convinced you that there's at least some level of tension there. And I've also shown you some evidence that these UDGs reside in core dark matter halos. So I think just by studying this one population of large low surface brightness dwarfs, we can actually start to answer many of the main problems currently plaguing our simulations of galaxy formation in this regime. I should say, if you'd like to use any of the data I've talked about throughout this talk, I'm now starting to maintain a catalogue of UDGs and spectroscopic properties on my GitHub. So currently there are 33 UDGs that meet the UDG definition, points 1 and 2, and have a spectroscopically measured velocity dispersion and or spectroscopic stellar property and population information. So I'll scan away, don't ask me for it. And just a quick little what's next. So if we're going to keep pursuing this field and look into it in more detail, we need to really start measuring the mass profiles for these globular cluster-rich UDGs, and even beyond UDGs to things that are just globular cluster-rich for their stellar mass, because we know that this definition is quite arbitrary. To accurately constrain their stellar mass-halo mass positioning and really be absolutely sure that there's something wrong with our models and that these dark matter halos that we do not expect to exist do. We need to start measuring more masses and metallicities for globular cluster-poor UDGs. At the moment, a lot of the science is focused on the extraordinary, very globular cluster-rich things because they are so unexpected. But in doing so, we haven't built a good comparison sample of the things that are expected. And we also need to start measuring the masses and metallicities of more field and group objects so that we can probe these evolutionary links with the cluster samples. And so that's why I'm very excited about the cosmic reionization mapper that's just been started to be commissioned on the Keck telescope this semester. But also I think it's important to note that this is very, very key science that can be done with MUSE. MUSE is excellent at getting the entire globular cluster population of these galaxies. And so if you're reading the ESO proposal I just submitted 2 days ago, please read it well. So these are my conclusions. I think it's quite obvious that UDGs are a very non-negligible population across all environments. The evidence at the moment suggests is that 5 to 7% of all galaxies, not just dwarf galaxies, but all galaxies, are ultra-diffuse. We have very reasonable evidence that some of these UDGs reside in massive dark matter halos. Simulations are having a very terrible time reproducing them. Globular-cluster-rich ultra-diffuse galaxies do not seem to be an evolved population of some of these field objects that we're forming, unlike some of the ideas. But we actually do have some really good evidence that I think that they're these passive relics of this Z=2 galaxy formation. They're a galaxy that was destined to be something much more massive and failed. And so, to finish on a pun like I started, the future of this faint science is bright with large IFUs. Sorry.
Thanks, Jonah. Any questions online, Nandini, or in the room? Oh, yeah. Go ahead.
Me? Okay. Great talk, Jonah. So I have a very naive question. So with the help of those fancy telescopes, how much of the missing baryon problems can be solved when we detect these diffused galaxies?
So we talked to Simon Driver about this because he was very interested and kind of asked him the question, how much extra stellar mass are you adding in the universe by adding these galaxies? And I think the answer is, as a function of the total stellar mass in the universe, it's not a huge amount. Most of that, just by order of magnitude arguments, is tied up in much more massive galaxies. So I don't think it helps us too much with the missing baryon fraction, unfortunately.
I had another question related to your master light ratio plot. What is going on with the two dwarf galaxies associated with NGC 1052? They have a lower master light ratio compared to, I think, normal galaxies.
You clearly don't follow Twitter, Nandini.
Yeah. So there are. So I would almost claim that these two 1052 galaxies are the most controversial galaxies in astrophysics of the last 5 years. I think since the first discovery paper of one of them in 2018, there's been over 300 publications related to one or the other of them, including 2 Nature papers and various rebuttals of Nature papers. When the last Nature paper of them was published 2 days afterwards, I think there was a rebuttal of the Nature paper that had already been on archive. So there's quite a bit going on, to be sure. The evidence suggests that the velocity dispersions we measure for these galaxies are consistent with that you'd expect from just the stellar mass alone. There has been some controversy about whether or not they're actually in the 1052 group or whether or not they're closer. They're closer, you can allow for more dark matter. Personally, I think that's been settled with a ridiculous amount of Hubble time that went into resolving stars in each one of them and putting them at the further distance. The next question is, how do you end up with 2 galaxies that are dark matter deficient in the same group? And the other thing that these galaxies have is they actually have very, very bright star clusters. And it's something that's almost not observed in any other galaxy in the universe. Almost all galaxies have a very well-established globular cluster luminosity function. It's Gaussian, it has a very set peak and width. Whereas these 2 galaxies seem to have a significant population of very, very bright globular clusters. And so that poses another puzzle where you have these 2 galaxies with these 2 very extraordinary properties that aren't seen anywhere in the universe, but in the same group together. And the hypothesis currently being tested is that they might have formed by 2 things smashing into each other, and you form 2 galaxies like that. It has received quite a bit of negative feedback, I'll be polite, in the community. But at the same time, there doesn't seem to be a very good alternative explanation as to why there'd be dark matter poor, these very bright, luminous globular clusters. So,
Thanks.
I had a question just about kind of in your systems, how do you go about counting the globular clusters? Like, do you use kind of automatic / machine learning type techniques? And how in the clusters do you say it belongs to that galaxy and not to an intra-halo population?
so the first order, what you do is you make a kind of size cut, depending on the distance, they're either unresolved or partially resolved by HST. So you cut for everything that's point sources, and then usually you get two different filters, and you can make a color cut to say that they have the right color to be a globular cluster. After that, you tend to just do a point source distribution as a function of radius. And so if they're associated with the galaxy and not kind of the background of a cluster, you expect to see it fall away. And you can integrate under that and get an estimate of the number. Happy.
There was a rumor of hand counting coming from a particular workshop, which was concerning to
Oh
me.
no, that was I was at the workshop. Yes, that was done. There's another controversy about how many globular clusters these galaxies. There's quite a lot of controversies in the field. Yes, there was certainly a. Please raise your hands if you think it has A or B. At the workshop. Thank you.
Thanks, everyone.
Let's thank Jonah again.
Oh yeah, thanks, Jonah. And also, it's usually lunch after these seminars, and we have Solar Origin gift cards very kindly provided by Caro to pay for both the speaker and students. Sorry, sir.
Nice to meet you. I've actually brought my